So there were some complaints about the last lecture. The complaint was that actually it took me 2 hours to get to Hello World. Which is true, right? Which is true. But my excuse is that rather than just simply starting teaching you Haskell, I had to do like an hour and a half of unteaching, right? Imperative programming. So I hope now you are in a better state to start absorbing functional programming after being untaught imperative programming. So last time we talked about functions, and we haven't even touched the subject. There's so much more about functions. So today we'll concentrate on coding, and we'll concentrate on functions, and if I have time, I will start with data structures. Okay? So, you might remember from the last time, it's something like F, A, B. Always the first thing is a function. The other ones are arguments to this function. When we are making a function call, that's the syntax for function call. And if we are defining a function, then we put an equal sign here and some expression here. Okay? So it's kind of wrong to put parentheses here, right? Just like in regular languages. But it's all only kind of wrong because the compiler will not complain. Well, it will complain if it doesn't match the definition of the function. But we can define a function. Remember, we were defining the function square distance. Square dist. And we are giving it 2 arguments, x and y. Right? This distance from the origin. But we could as well do this. And the usual definition. X to the power of 2 plus y to the power of 2. Hahowever, this is completely different. Okay? And if you want to call this function, you will have to put stuff in parentheses. SQ dist of, let's say, I use 3, 4. Now, what this looks really familiar, right? But it actually means something else in Haskell. It means this square distance actually accepts a pair, one argument. But this argument is a pair. Okay? I could have written SQ dist of a pair. Let's call it P, right? But then I would have to extract x and y from this pair, which is okay, it's possible. I can say first P, that's the first component of P, which will be x, plus second P. Okay? So, what's the difference between these two? Here, I specifically, I didn't split the pair. Okay, I just said this is one argument called P, and I can call functions first and second on this P, past P to this. These are called projections, right? And I can extract stuff. This is all defined in the library, in the standard library. But this is a different form. In this form, this is a pattern. So I'm extracting stuff from a pair using a pattern. This is a pattern that matches a pair, right? And extract x and y from this pair. So it's sort of, there are these two styles of writing functions in Haskell. One is that you immediately do pattern matching and you extract stuff. or maybe partially pattern match and extract some stuff and then do more pattern matching and so on. Or you just specify the argument without unpacking it, without patterning it, without pattern matching it, and then you extract it in your code. Okay, so main in this case, if you remember main, would be equal print, and we'll put parentheses here. Okay? Now, maybe you should start writing this stuff so that if I make a mistake, it will be immediately obvious.
I'm Bob, yeah. Beautiful assistant.
I think Haskell is the assistant. You're just a typist.
Okay, so you can just open a file like previously, right, and just put this definition in square distance with this pattern, and then write main to just test it, right? So this should print 25, as we remember from the last. Now, the problem with this notation is, I mean, it's fine as long as we don't have too many parentheses, right? But it's kind of looking like Lisp, right? Parentheses, 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 and so on. So there is a way of avoiding these parentheses, and it's very interesting, okay? Because we don't need any built-in sub-language to avoid these parentheses. What we can do in Haskell is just in the library define an operator. This operator is called $. Okay, and instead of putting these parentheses, we just put a $sign here, and we say sq dist, put another $sign, and say 3, 4. Okay? It's the same thing, except that now we are using a $sign. It's an operator. Okay? And you remember when we were talking about syntax of functions that the space between arguments and between function name and the arguments, that these spaces can be sort of thought of as operators, right? They bind the tightest possible. This is the tightest binding, so you don't need any parentheses, and they associate to the left, right? Now, $sign is like the total opposite of space. So this is also function application. Space is function application, and this is function application. But it has a completely different properties. Namely, it binds very, very lightly. It's actually the lowest possible binding in Haskell. Although you can define other operators which have the same binding strength. What does it mean? It means that anything binds stronger, so I can put expressions here and stuff, and they will stick together between $signs. Okay? And also it associates to the right. So the first thing will be evaluated. So like if I have print $ and the rest will be evaluated before calling print. Okay? And then this will be evaluated, and it means this, since there's a $sign, it means this function will be called with this argument after this is evaluated. So it will first create the pair, then pass this pair to square distance, get the result, and pass this result to print. Okay? So this is very common syntax in Haskell if you want to avoid too many parentheses.
Question.
Yeah. Oh,
So I
okay.
have a totally unsolicited comment,
All right.
which is that I love dollar signs, but they cause me more trouble than anything. Parentheses work really, really good.
Okay, well, that's fine. It's fine. Yeah. Well, that depends on your style, really. Yeah. Some people prefer this, but you have to be able to read this style because some people write in this style, and you have to be able to read.
It's good when it works.
Yeah. I mean, presumably they compiled it and tested it, so when you're reading, then no problem.
If you want your code to look like Lisp, go for it.
Yeah.
Well,
Alright, so does it work?
It does. Oh, there you go.
Excellent.
Return
25.
to going.
Excellent. All right.
No more questions.
More questions? Yes?
What evaluates if you remove the last dollar sign?
Okay, so suppose that we remove this last dollar sign, right? Nothing. It,
Oh, okay,
it
so
works.
That works as well, yes.
It works as well. Yeah. But if we wanted to like say more stuff, well, this is such a simple example, right? But if we had like stuff that has some, let's suppose that we could add these things, right? Then the addition would be done first, and so on, right? So in this case, redone. Okay. Good.
You're not following along.
So we have these two opposites of precedence, right? The strongest precedence was this one when we had the SQ dist with spaces X and Y. These guys have the strongest precedence. They bind very strongly. With dollar signs, they bind much weaker. Totally, the weakest possible. So what it means is that if I put other, operators here, times 3 and plus 1 and so on, this is a unit. So everything between operators. Why is it so? Because all other operators have the precedence that's in between. There are like levels of precedence. I don't know how many. 7?
7, I think.
7 levels of precedence in Haskell. And when you define your own operator,
then you get to have
you can specify what level of precedence and whether it binds to the left or to the right. We'll see examples of this later. So let's do a little exercise. And Richard will do this exercise after I explain, right? So first let's the audience try to figure out. So let's define a function square. It just squares its arguments. Square of x equals, well, let's write it x times x. Okay? I mean, we say x to the power of 2, but x times x is fine. Okay? So what would this do? Main equals print $. So I use $sign a lot after print because I don't want to put everything in parentheses and I might forget the closing parentheses. It's like after print you usually do this. So what if we do this? SQ of 2 plus 3. Okay? Is that correct? What do you think it will print? 7. Why 7? Because SQ will bind with 2, right? That's the strongest binding. Operators have lower binding, right? So it just separates the stuff on these operators. So we'll calculate square of 2, which is 4, plus 3 is 7. So correct, right? Now we probably meant this, right? That makes more sense. Okay, so these exercises in precedence are really necessary in the beginning. After a while, you get it and you don't need. But it's not totally obvious when you first look at it. Right?
So can you or can you not use the dollar sign in place of the 2 plus 3 parentheses?
That's a good point, right? You can, right?
Yeah.
Can you check it?
There you go.
No, okay. Excellent. Yes, because then 2 plus 3 will be executed first, then the square of this result, and then print of this number. Good point. Yeah.
Question. So the dollar sign does it run only until the end of line or until the end of the expression?
Well, since it binds to the right, it really works till the end of the line. Right? Because everything that's after the dollar sign will become the argument to print, right? So all this stuff becomes the argument to print. And then we look at this and we say, okay, everything after the dollar sign becomes argument to SQ.
So if I do plus 3 on the next line,
Will it still work? Well, it's a tricky thing because their indentation in Haskell is important, right? So if you don't indent it, you have
That
indented,
will work
right?
because it has an operator at the end of the line, so it's unambiguous to the parser.
Well, so you have indented 3.
I have indented, that's correct, yes. If I don't indent, I'm not sure. I suspect that will not work. Let's try it and see. Yeah, parse error.
Yeah,
Incorrect.
see? So you have to indent it, which means you are continuing the stuff. But if you indent it, then you can cut after the operator and it will work.
This won't work because it's move the operator onto the next line. Oh, that does work. Surprised me, but okay.
Will this work?
Don't write code like that, no.
Square of minus 1. What's square of minus 1? Plus 1, right? No, it won't work because even though I wrote it so tightly here, really, the minus is here in between and it just says, okay, so you want to subtract 1 from this function, right? How do you subtract stuff from a function? So you can't do it. You have to put, this is like in the beginning you make errors by forgetting to put parentheses around negative numbers. So just remember, negative numbers, put parentheses. Okay, now let's define a function that actually calculates distance, because this is square distance. The one we used before was square distance. So let's use distance, and we'll pass it a pair. Okay. So this is the notation with a pair. We'll say pair is like a point in 2 dimensions. Let's call it PT. Right? So this is the definition of distance that takes a pair. Okay? And we'll define it as square root. That's a function that's in the standard library, which is called prelude in Haskell. So this is a prelude function. And we want to apply this to square distance, which we had previously, of PT. Okay? So this works. Right? But you have to put a pair there. Square.
Oh, right, you're doing using a pair. Yes.
Square distance of a pair. Yeah. So we have these 2 square distances, and we'll just be switching between them. One takes a pair, the other. You cannot have both at the same time. But we'll be just switching. So this works, but it's kind of awkward. There is a simpler way of writing this. Because what we are saying is that there is a function called dist, okay, that is equal, these two functions applied one after another, SQRT, and composition of functions has a very simple denotation, dot. Okay? These two things mean exactly the same, but now we are saying this function is equal a combination of these two functions, right?
You gotta print it.
So once you apply this to a PT, right, you get this one. But this is a much nicer notation. Well, some people say much nicer. Some people say this is unreadable. No, this is called, and the funny thing is it's called point-free notation. Why? Because it has a point. Crying out loud. Why is it called point-free notation? Well, okay, it comes from mathematics where point is actually like you're calculating a function at a point, which means you are passing it an argument. So this is the point. Well, I called it a point. So this is point not free notation, pointful notation. But here I don't specify for which point. I'm specifying a function as a whole, like, you know, holistically.
So in the first expression, it's not obvious that you're composing two functions. And in the second expression, it's explicit that you're composing two functions.
It's explicitly composing two functions. Right. So there is this dot, which is an operator. Right? It's a very tiny operator. Probably the tiniest operator in the world. Just a dot. And of course, the question is, what's the precedence and what's the associativity of this operator? These are the first thing we ask about every operator. So the precedence is very high. It binds almost as strongly as function application, which is definitely the strongest possible. So this one has high precedence, and then it's only one notch below function application.
So then if you had an argument after square dist in this dist equals blah blah blah, then does that mean that square dist would be applied to that argument first and then it would attempt to apply the composition?
Okay.
The opposite.
Well, but what's the argument there? Is it a function application? Then the function application will definitely bind stronger. So if you said here SQ dist
In some pair.
prime of some 3, let's say, that would still give you a function. Okay, I'll talk about currying later, but this is still a function. And I could do. I mean, this doesn't make sense, but the thing is that this would bind stronger than this. Function application binds stronger. But anything else is weaker. So if there's like a multiplication or plus.
Now, remind me, in Haskell, can you have many functions that have the same name?
No.
Okay.
Well, okay. Not simply like this. Okay. You have to have a type class.
Okay.
There's no name overall.
There's
Right. Because if there were, then this expression becomes very ambiguous pretty quickly.
Yeah.
Yeah.
Okay. And the way to read it, and this is very important because this is confusing, especially for F# programs, right? Because in F# you would say this is SQ dist and then SQRT, right? Do people know F# here? Well, it's sort of like a pipeline. First apply this function, and then the result of this function pass it to SQRT. And here's the opposite. First apply SQDist, and then pass the result to SQRT. That's the meaning of dot. right? And this is pipelining also, but it's from right to left, and this is pipelining from left to right. Some people find this much more natural. I mean, you can define an operator like this in Haskell as well. People don't. This is a mathematical notation. I mean, in mathematics, this is actually a little circle for function composition.
If I add a composed function to the right of square dist, what's then the order of computation?
If you put another dot here, right?
Yeah.
Yeah. So that's the next thing is what's the associativity of it, right?
Doesn't matter, right?
No, it matters.
To the right, right?
What? they're the same, right? It's functional language.
No, because the types might not match. Your function on the right hand side might be int. You're returning string, so you have to apply something to it that.
Takes a string.
The thing is that the dot is associative.
Yeah.
It is
Yeah.
associative, right? So whether you put parentheses here or there
Doesn't
matter. But strictly speaking, I think as an operator in Haskell, it is right associative.
Okay.
And if I'm wrong, please correct me. Who here knows Haskell? So I was right. Okay. So maybe this is a good idea. Ask GHCI, right? How do you ask GHCI? You say :I, which is for info, and if you want to apply it to an operator, you have to put this operator in parentheses. Now, putting an operator in parentheses turns it into like a regular function, right? Because an operator usually is, well, not always, but it could be infix. This is an infix operator. So it takes two arguments, but one is on the left, the other is on the right. If you put it in parentheses, then both arguments go in front, just like a regular function. So it's a funny named function.
:T requires the parentheses, :I does not. I don't know why.
I doesn't require parentheses.
Try it. Okay, yeah, they're both.
Ah, interesting.
And there are 9 levels of.
9 levels.
And then enlightenment.
Well, yeah. I mean, you don't have to remember this stuff because you have GHCI. It will tell you. Okay, cool. So this is infix 9. So actually there are 10 levels because then the space, right, the function application is the 10th level. But nothing else can be 10. So it's not kind of not visible to the user. The user can go up to 9. Yes?
So does the right argument contain any number of arguments? Function on the right dot.
The function on the right, as long as it produces a function, okay? Because what's on the right of dot is a function. See, so okay, let me rewrite this. So dot. What's the type of dot? If you do colon type of dot, what you get is it's okay. So in this order, okay, whatever. Well, I'll write it in a different way. You have a function. So the first argument, the one on the left, is from A to B. The second argument is a function that goes from. Well, okay. Let's better do this B to C. Okay, so that we go alphabetically. A to B, and the result is a function from A to C. Now here I have to put parentheses. Here and here I have to. Here I don't actually. So what the compiler says, oh, it's just this, right? Because this is right binding. Right? But we'll put parentheses anyway because that's more readable to humans. It means it takes two functions. So one argument, second argument, result. One argument is a function from B to C. The second argument is a function from A to B. and it glues the b's together to get a function from A to C. Is that correct? Yeah. So a picture is better, you know. This is A, this is B, and this is C. So you have one function from A to B, another function from B to C, and you get a function directly from A to C. That's composition. Okay? Now these orders here you have to like, no, maybe other.
But
Yeah.
that function from A to B, would that be like an A1 to A2, like a function that takes two arguments? I mean, it seems like it should still work, right?
Okay, we'll talk about currying next, and this will explain that a function of two arguments is really a function of one argument that returns a function.
But even if you didn't have curry, right, mathematically you could do that.
Doesn't make sense.
Composition is difficult if you allow more than
One argument.
one argument. But it doesn't generalize well.
First, like the innermost application, like ends up being the argument to compose.
That's correct.
Well, the argument to compose must be a function.
Sure.
So,
Right.
if you have a function that takes a bunch of arguments and returns a function, then you can put it there for composition, because it returns a function.
We have to return a value.
No, it's really, this is the beauty of functional programming, that you're operating on functions without arguments. This is point-free thing, right?
Okay, so let's think about a trivial but illustrative example, right? So maybe make an identity function,
But
right?
that's the next thing.
Yeah.
Okay, I have it here. Okay, so the identity function, that's a unit of composition. Okay, so if you think of this composition as some kind of multiplication, right? Because it's associative, just like multiplication, right? And does it have a unit? Is there a function that if you compose it with another function, you'll get this other function back?
Like you say, identity.
That's identity. That's a function identity. And in many languages, defining identity is actually extremely difficult because of these, argument passing conventions, by reference, by value, by move, by, const reference. Anyway, so ID is a function whose signature is from A to A, so it has, takes from any type to the same type, right? And its implementation is also very simple. ID x equals x. So whatever x you pass it, it just returns it back. So it doesn't change anything. It just takes an argument and returns it back, right? No transformation whatsoever. So a function that does not transform anything is an identity. Yes?
That's what's actually cool about the type system. This type tells you we cannot do anything but that.
Yes, that's a good observation. Once you specify this type, A to A, there is no other possible implementation. What? Yeah, and we don't have side effects, remember? This is a pure function.
There are lots
And-
of functions from type A to type A.
If they have
Yes?
different
Really?
strengths, then you
Give me one.
Yeah.
You could return like bottom
From
or
any
something, right?
specific type A to type A.
Yes.
You don't know what.
Yeah.
But
For a
it could work
specific,
any
right?
type.
But
Yeah.
here A is a type variable.
Unconstrained.
Okay, so what it means is actually it's a polymorphic function. Okay, when you have a type variable in the signature of a function, it means it's a polymorphic function, and in Haskell, this polymorphism is actually totally general for any type A. I have this function that works for any type A.
You could return undefined, right?
It's called parametric polymorphism. Okay, let's not talk about bottoms.
So you couldn't have a function which is the identity as we know it from any A to any A, except for int to int is minus. And that would not have the same, that would not have that signature.
Okay, that's a good point. Right. Why not have a function that returns x for everything, but if this
it's an
is an
integer.
integer, that it changes the sign.
Yeah,
Okay.
would that not have
Yeah.
the same signature?
From
No,
an internet.
It'll be int to int.
you are talking about a function from int to int. Then.
There's no possible signature for the function.
Okay, but this is a deep question, really, because this is the essence of polymorphism, parametric polymorphism in Haskell. So when you say A, you know that the function is from A to A, you say one formula works for all of them, right? So this is a function that one formula defines this function. And this formula is this. Right?
And that formula is not allowed to ask if A
No.
is equal
That
to int?
would not be parametric polymorphism. That would be called ad hoc polymorphism.
Oh my goodness.
Yes.
What did you call it?
Ad hoc.
Ad hoc, right, yes.
Ad hoc polymorphism. And you can have ad hoc polymorphism. It's very useful, right? But this is not it. You can have ad hoc polymorphism in Haskell with type classes, for instance.
And that would have a different signature. So my
Yes.
function ID prime does not have the signature A to A.
No. No. And the trick is that it has to be the same formula for all times. Okay? And that's really hard to come up. And this is called theorems for free. There's a paper by Philip Wadler, Theorems for Free, in which he proves, actually Reynolds first proved this, but then Wadler picked it up and translated to Haskell, that parametric polymorphism that says one formula for all actually leads to this additional theorems that you can just derive for free, and they are just like, yes?
Good forcing evaluation of x is different than returning just x.
Forcing
Evaluation of x, in the ID function. The Haskell is lazy, so if you don't do anything, it does nothing. But if you force evaluation, it still returns the same thing, but it's forced.
But forcing really does not influence the semantics.
Unless X throws an error.
Yeah. But let's not talk about that.
Sorry.
Errors would be part of the type, though, right? It wouldn't change the type.
But it will change the semantics. If
No,
it is-
it doesn't. Errors don't change the type. What errors do is, if you have to take into account that the function might not terminate, then actually it influences your type system. So it's much deeper than that. It says every type must contain the bottom type. Okay.
So suppose we made an identity, a recursive identity that called itself,
Yeah.
right? It would never terminate,
It would never terminate.
right?
Yeah.
But I think that the type system would probably work out the fixed point and would allow it.
ID was ID.
Yeah, so you can have an int to loop as the
What's
Yeah.
the type of ID?
Try it, Richard.
Alright, let's see what we do.
It should be void.
Well, we'll not come up with a new name
We'll
for it.
talk about
Foo.
it.
Let foo equals
Okay.
foo, what happens? Alright. Let's, well, I'll look at that. I believe,
Right, but what's the type of food
oh yes,
is the
the
question.
all important thing. T.
Is that a kind or something?
It's just, I don't know what that is.
Without argument.
It's a value. It doesn't have any
It's not a
accuracy.
kind, it just doesn't have any qualifications on what the type is.
Why wouldn't it say A instead of T then?
Alright,
Ah,
It's the same thing. It's just a type variable.
So what if we have
Okay.
foo takes x equal to
We,
x
we,
equals
we have to really go
there you
lower
go.
than that, okay? Because we are getting into a very theoretical discussion here, okay? Which I would love to talk about these theoretical issues, but we are now learning Haskell just to be able to do parallel process.
T
Okay?
return some type of T1 as long as it's not bound to something else.
Okay, let's go back to this. So you understand that ID, when composed with any function, whether it's on the left, like pre-composition, or on the right, no, on the left will be post-composition, on the right will be pre-composition. Okay? It will give you back the same function. So it's an identity. And what we often call this stuff that's associative and has identity, we call it a monoid. But we're not going to talk about that. One more thing about how do we pronounce this, okay? The way to pronounce this that's really useful is to say after, okay? So it's square root after square distance, okay? Because we are applying it after we applied square distance. So once you realize
clever,
how to
Bartok.
pronounce it, you know, it kind of it makes it much easier. So remember to always pronounce it after.
Is there a way to pronounce dollar sign other than dollar sign?
First.
Is there a name for a dollar sign?
Before.
Apply. I think it's called apply, isn't it?
Yeah.
Sort of. But
think
apply
that-
has many meanings. So.
I think of it as dollar sign, but it's kind of like an S for space, right? It's kind of like a poor man's space.
And in Europe they call it euro. Okay. So.
Was he kidding or no?
So this is a great thing that in Haskell you can actually operate on functions like if there were, you know, regular things. You can compose them, you can apply operators to them, you know, you can create new functions from old functions. And one of the things that you can do with functions is currying to create other functions from old functions. But before we get to currying, one more thing. Let's do a little exercise. How would we define a function? Let's call this function flop. And it's supposed to take a pair of two things and return this pair but reversed. Okay?
Not flip.
I'll call it flop. Because if I call it flip, then it will
Oh, yeah.
be from prelude. Prelude has a function. Now let's get a flop. So first of all, what would the type signature of flop be? What argument does it take?
Pair to pair.
So it's pair to pair.
Pair of AB to pair of BA.
Okay. But you already know Haskell, right?
Maybe.
Somebody who doesn't know Haskell. What should it be? Pair to pair. Pair of what? Pair requires two types, right? So it's an arbitrary pair of two arbitrary types. They don't even have to be equal. It's pair of A and B, two type variables. You know? So that's the argument. It takes one argument, a pair, right? And returns, what does it return? Another pair, right? But what are the types?
B and A if we're swapping them.
B and A, because we are swapping, right? B and A. Okay. How can we implement it?
I think we already have.
I kind of did, right? But this is an equation on types, right? Specifies types. Now we're talking about values because so flop takes a. So we have two ways of doing this, right? We can say flop takes a pair P, and P corresponds to this. Yeah, let's try this. Let's try this first, okay? flop of P. Now what does it return? It has to create a pair, right? So it will return a pair. What should the first component of this pair be?
The second component.
The second component of P. So to get the second component of P, we call the function SND of P. And of course here we call the function FST of P. Right? And that's it. Now probably most Haskellers would not write it this way because they like pattern matching. Pattern matching is so nice. Well,
Yeah, but it's the opposite of point free.
yeah.
There's still
Yeah, you could probably write this as in point free, but let's not
I
go
mean, that
there.
is the point
Okay.
free notation.
No, it's not because there's a point.
Oh.
No,
No, but you can write that
point free would be. I think this would.
Oh, yeah, it's flip.
No,
It's
no.
flip. It's flip.
It's
Parens, comma P. And then you take the P out. Yeah. Your pipe.
Flop is
flip
defined in terms
the-
of flip.
Yeah, I think you. Yeah.
Okay.
If you want to be really
Okay.
ridiculous. It's like that, right?
Yeah, actually, flip means something else. Flip means reverse the arguments to a
That's
function.
why I called it flop, by the way.
Yeah, okay, you're right. That's why I called it flop. I forgot. So we would put a pattern here and say x, y, okay? Match this pair to its components, x and y. So this is a pattern. Right? And then you can simply say this is y, x. Just reverse them. Pattern match and create it. Right? That should be, is it simple? Does it work?
Second comma.
That works, yes.
Alright.
The flip version didn't.
Yeah.
I don't.
So he applied flop to a pair of integers, right? Which is good. But you can change the second one to a string, for instance, right?
Totally, yes. Let's do that.
Yeah. You can say print
Yeah.
flop, let's say 5 below. And it will work too. Well, because these types are polymorphic, you know, so and we never used the type. We never did any operation on these things, so we don't have to specify. You know, they can be anything. It can be integer and string. And we'll just reverse them. Right? Did you do that? 200 and a half. Okay. Okay, good. Excellent. Okay.
Yeah.
So now, let's talk about currying. And by the way, all these things actually have application in imperative programming too. It's just that people don't learn this for some reason. And, well, they try, like template in C++, you know, template metaprogramming. They actually do have currying, but it's a template. It's a generic function. It's rather complicated.
I'm going to say
Haskell, it's
first.
just. Oh, he's writing C++. Okay.
Here.
Oh, but you're passing by reference? How do you know you can tell?
So Richard, that flip comma works, but it doesn't take couple, it takes individual arguments.
Right. Currying is what we're getting onto right now.
Yeah.
Yes.
Okay.
You
Makes
uncurry
sense.
it.
So let me write the square distance again.
Totally.
This is my workhorse function. So at some point we defined it. We just forced it to be double. I mean, the compiler says that you can use it for more general types, but let's just do this, you know. So this is squared dist that takes x and y, and x squared plus y squared. Yeah. So that's this one. Now, if you look at this, and I already told you this is kind of funny notation. Why do we have these two arrows, right? Why not separate these things nicely and say these are arguments and this is the result? Because it's not really true. Because you can partially apply this function in Haskell. You can say, okay, so what's SQ dist of, let's say, 0? Okay. I applied it only, I gave it only one argument. It's a function of two arguments. I gave it only one argument, right? So I gave it this first one. So look at this and put parentheses here. Because we said these parentheses are possible, they are redundant because it binds to the right? But so we usually don't write them. But if we want to, we can put parentheses there. And now the interpretation of this, you just look sideways at it and say, okay, it's a function that takes a double and returns, what does it return? A function. So it's a function that takes a double and returns a function from double to double. Okay? And this equivalence, is the essence of currying. That you don't have to in Haskell, like in other languages you define a function of two arguments as different beast than a function of one argument and so on. Now in Haskell it's enough to define what you mean by a function of one argument, and everything else follows from currying. So if you want to have a function of two arguments, well, just define a function that takes one argument but returns a function that can be applied to the second argument, right? And in notation, whether it's definition or function application, there's no difference in notation unless you insist of putting some parentheses that are redundant. There's no difference. So when you are defining a function of two arguments, the same as defining a function of one argument that returns a function. So dist of 0, what would the type of this be? Well, the type of this would be double arrow double. So you can take this and apply it to 1, let's say, and you will get it up. So you can partially apply, and then you can provide the second argument, and so we can even give it a name, like dist from 0. Okay, square distance. Square distance from 0. Equal. It's a function of one argument, right? And just equal to SQ dist with 0. If you can parse this, then you're halfway to understanding Haskell. Is that correct? That's correct.
Yes.
Yeah? Okay. So square dist of
There
0.
shouldn't be that y there,
You
right?
shouldn't divide the.
Or you should put a y after the.
Oh, sorry, sounds better.
Yes.
Good. You're getting it.
The point 3 now.
Excellent. So square dist from 0 is a function of one argument, right? Its type is double. I can put it here. SQ dist from 0 is just this, double to double. Right? And you see how it works? If I apply this to y, to some, let's say, 2, then it's the same as applying SQDist to 0 and 2. And now I can really explain why this crazy notation in Haskell that we use spaces in function definition or application is so useful. Because if you define SQDist as acting on a pair, then the carrying of this is not obvious. How would you supply one argument to it? So all these languages that use parentheses and commas, they have huge problems defining carrying or partial application. Like in the C++ library, there is, what do they call it? What is it?
Bind?
Bind!
Yeah, the standard
Bind. STD bind. Yes. STD bind is this complicated template that actually just fills one argument.
Placeholders and
Yeah.
that's
Oh, okay, so
everywhere.
it can actually do more. It can fill several arguments that are out of order.
Right.
Okay. They must be a little better than us. So in Haskell, when we want to change the orders of arguments, we call this function flip. It just flips the order of arguments. Must be like simple stuff. So this notation is not very convenient for partial application. And now the equivalence of these two, they are actually equivalent, right? They do the same thing, after all. Except that this can be easily curried, this cannot be easily curried. I mean, if you want to curry this, you actually have to apply a function called curry to curry it, to get this function. And it's okay, it's possible, right? But these two are absolutely equivalent. So this equivalence in particular is called currying. Now, applying a function of n arguments to fewer arguments, that's called partial application. And I sometimes confuse these two things because it's like all currying.
Sorry, so just to clarify,
Mhm.
or I guess to repeat, currying is the equivalence.
Currying is the equivalence of
Partial application is when you pass less argument than it can take.
Yes, yeah. Partial application is passing fewer arguments than required.